Hello, everyone. Welcome to PMTTT session 59 in July 2024. My name is Sang from University of Minnesota. I'm joined here by a member of PMTTT, Muhammad. And welcome, everyone. In this session, we have two exciting speakers from around the globe. Our first speaker is Dr. Ali Fatih. Um, he is a final year PhD candidate in chemical engineering in the multi-phase reactor group at Eindhoven University of Technology. His research focuses on the investigation of fixed packed bed and trickle bed reactors, utilizing magnetic resonance imaging for experimental analysis and core network modeling for numerical simulation. The title of his talk is Pore Network Modeling and Magnetic Resonance Imaging of Packed Bed Reactors. And Ali, floor is yours.
Thank you very much, Sang. So I will start the presentation. I also hello everyone. So my presentation is going to be about pore network modeling and magnetic resonance imaging of packed bed reactors. So I will start by general information about packed bed reactors. So packed bed reactors are one of the commonly used chemical reactor types in many chemical and petrochemical industries. In a packed bed reactor, there is a packing of catalyst particles through which a liquid or gas containing reactive components flow. The presence of the particle packing generates a vast reaction area, and also it enables controlled residence time distribution of the reactive component inside the packed bed. But it comes with a cost of high pressure drop and consequently high operational costs. Also, the presence of the particles hinders liquid or gas movement, and it causes flow maldistribution. Or in other words, the flow is not evenly distributed inside the packed bed reactor. This flow maldistribution could cause some problems. For example, in the case of highly exothermic reactions, it could cause hotspot formation and thermal runaway of the reactor. So a detailed understanding of the flow behavior and transport phenomena inside the packed bed reactor is quite important in optimizing the performance of the reactor and avoiding issues such as hotspot formation. So there are various parameters that affect the hydrodynamics inside the packed bed, such as physical properties of the fluid, such as density and viscosity of the fluid. The other important parameter is the packing configuration. The packing particles could be of different shape, such as spherical, cylindrical, sphericylindrical, and etc. And they can also be of different sizes. The effect of particle size and shape becomes important, especially in the case of slender packed beds. In slender packed beds, the column to particle diameter ratio is usually lower than 10. And because of that, we have intensified wall effects. So, and also these slender packed beds, they are preferred when we want to have a controlled heat management in our system. There are various numerical and experimental approaches to investigate packed bed reactors. We can categorize the numerical approaches based on the length scale of the model. One subcategory is the microscale method, and an example of it is CFD, or computational fluid dynamics. In microscale method, the computational unit or the grid cell is usually very small, for example, 40 or 50 grid cells per particle diameter. The other subcategory is the mesoscale method, and an example of it is PNM, or pore network modeling. In PNM, the smallest calculation or computational unit is 1 or 2 orders of magnitude larger than the one in CFD, and it makes PNM to be much more faster and computationally efficient compared to the CFD methods. PNM also is able to provide with partially resolved local results, of course not as resolved as CFD. It can also provide accurate results, but for that we usually need a need an initial calibration for the pore network model. And this calibration can be performed using CFD or experiments. Once the PNM is calibrated, it can be used for further analysis. There are also various experimental approaches to investigate the backbed, such as PIV, RTD, and advanced imaging techniques such as CT scan. One interesting experimental approach is magnetic resonance imaging, or MRI. MRI non-invasively scans optically opaque systems, such as a packed bed, and it not only provides us with information about the structure of the packed bed, but also it provides us with information related to the velocity distribution of the flow inside the packed bed, which makes MRI quite unique approach. In my PhD, I used these two approaches to investigate the packed beds, MRI and PNM. Here is a schematic of the experimental setup that we use for MRI imaging. The fluid phase, which is water doped with 3 millimolar gadopentadic acid contrast agent, is pumped into the packed column using a peristaltic pump. Here you can see a schematic of the packed column that we use. It has an inner diameter of 21 millimeter. There's also a porous plate in the entrance of the column to distribute the flow. Once the column inserted inside the MRI machine, the MRI imaging is performed. From MRI, as I said, we get two types of images. The first type is the structure image. Here you can see an example of the structure image. This is a cross-sectional slice from the column. The gray part represents the liquid phase from which we obtain MRI signal. And the dark circles here, they represent the particles. Another type of image that we can obtain from MRI is the flow image. Here you can see the velocity distribution of the flow inside the packed bed. And we can obtain it in fine resolutions. For example, here the voxel size is 200 microns. For structure imaging, we use a flash 3D sequence of MRI, and for flow imaging, we use a PCGRE sequence of MRI. In our previous work, we used MRI for investigating a trickling gas liquid flow inside the packed bed. And we categorized the trickling flow using parameters such as phase distribution. For example, we can say how much of the column is occupied with liquid, gas, or particles. We were also able to calculate the local particle wetting, and also we were able to measure the local liquid velocity field. So if you want more information about this work, I would ask you to refer to our recently published paper. The numerical method we use is the pore network model, or PNM. PNM simplifies the 3D complex porous structure into a network of pore bodies and throats. The first step in pore network modeling is to extract the pore network from a 3D image, and this 3D image can be obtained using MRI. The method that we use for extracting the pore network model is the maximal ball extraction method, which is developed in the Imperial College. Here you can see a schematic of the pore network model, and the spheres represent the pores, and throats are represented by cylinders. And we use this pore network model to implement the numerical simulation on the packed bed. A pore throat pore element is the smallest calculation unit in the pore network model. Flow moves from pore I to pore J through throat IJ, and it undergoes energy losses because of contraction, constriction, and expansion of surface areas. The overall pressure drop from pore I to pore J can be attributed to these three losses. Here, N is the contraction curvature factor, M is expansion curvature factor, and F is throat radius correction factor. In P and M, we simplified the throats to have cylindrical shapes, but in reality, they have more complex shapes. So in order to take this oversimplification into account, we multiplied the throat radius by a factor called F, or the throat radius correction factor. In our Pore network model, we use M, N, and F as calibrating parameters of our PNM. By formulating the mass balance and energy balance equations for the pore throat pore elements in the entire network of the PNM, we can calculate the pressure values inside each pore and flow rate values inside each throat. Yeah, in a recent study, we have performed PNM of standard packed beds filled with spherical particles with different diameters. We calibrated the PNMs by fitting the overall pressure drop from the Pore network model to the ones obtained from a PRCFD approach for a range of Reynolds values. And we obtained these values for M, N, and F for these Pore network models. By comparing the local flow fields from PNM to the one from CFD, we saw that PNM is able to capture effects such as flow channeling in a good comparison with CFD. So in the rest of our studies, we use these values for M, N, and F for the RPNMs. So here you can see a structure image of the packed column imaged using MRI. So from this 3D structure image, we can obtain PNM. Yeah, we tried this, but we noticed that because of resolution limitation of MRI, the obtained Pore network model was not of high quality. So we decided to do another approach. We applied a particle detection algorithm on this structure image and obtained the position of spherical particles and reconstructed it by using the information regarding the position of the particles, and obtained higher quality images from the bed and extracted the Pore network model from it. And hydrodynamic analysis is performed on these PNM. So in order to compare the results from PNM to the one from MRI, from a specified volume of the packed bed, we obtain the flow images. Here you can see a schematic of the MRI flow image. The top part shows the velocity distribution in a cross-sectional slice perpendicular to the main flow direction. And bottom part shows the velocity and distribution from the side view of the column. Here we can see how the presence of the particles change velocity distribution. And especially close to column wall, we are observing high velocities, which are indicating flow channeling close to column wall. In order to quantify it, we decided to plot average radial velocity and flow profiles using both methods. Here you can see radial averaged and dimensionless velocity profile plotted against dimensionless distance from the column wall. So here values close to 0 corresponds to the wall region. We can see that in the radial profile of PNM matches quite nice with MRI. And also we can notice that close to column wall, we are observing high velocities. In order to investigate this in more detail, we plotted the cumulative dimensionless flow rate profile. Here we can see close to the column wall, around 40% of the flow is passing from the wall region. So we quantified the flow channeling there. And this is captured by using both PNM and MRI. So until now, we only discussed the Pore network model extracted from the packed bed. Now let's assume that each catalyst particle is composed of 10,000 randomly positioned microspheres. By doing so, we will have a particle model that accounts for the porosity, shape, and geometry of the particle. By extracting the Pore network model from this catalytic particle, we will have a particle scale PNM. And by using this particle scale PNM, we can implement intraparticle transport phenomena in our model. Now, let's imagine that the diffusion is happening through throats and reaction is happening inside the pores. Here on the right side, you can see a concentration map. The outer region of the particle has a concentration equal to 1. The species diffuse inside the particle and they undergo reaction. This, the reaction rate to the diffusion rate can be characterized using a dimensionless number, which is called Thiele modulus, or phi. Another important dimensionless number is the effectiveness factor, or eta. So the effectiveness factor shows the ratio of the reaction rate inside the particle with respect to the reaction rate inside the particle when the whole interior volume of the particle is exposed to the boundary condition. So for a special case of first order reaction, vacuum diffusion, and fully exposed particle, there is an analytical solution. And we calibrated our particle scale PNM with the analytical solution. Here you can see the radial concentration profile inside the particle and the comparison with the one obtained from the analytical solution. We can see that there's a really nice match between the concentration profile from PNM and the one from analytical solution. So the nice thing about our particle scale PNM is that we can impose a partial boundary condition on our particle scale model, which is prevalent in slender packed beds, as I showed earlier, that there's a flow maldistribution. So not all the particles are exposed to a similar boundary condition. For example, here you can see that the quarter of the surface and here half of the surface is exposed to a concentration equal to 1. Now we can use this to couple the particle scale PNM to the reactor scale PNM. Here is a schematic of how this coupling happens. For example, here we can see the top of the particle corresponds to a concentration equal to dark red. And we can see here that this part is in contact with the reactor scale pore, which also corresponds to a dark red concentration. So it's true for the orange part and also the blue part. So how we facilitate this coupling? For doing the coupling, we developed a new method by using the surface fragment. So we sliced each particle's surface into hundreds of surface fragments. Here you can see a surface fragment colored in orange. By locating the center of each surface fragment in the volume element map of the reactor scale PNM, we can see that which pore in the reactor scale PNM it is adjacent to. For example, here in figure B, we can see that surface fragment colored in red corresponds or are adjacent to a different reactor scale pore compared to the ones colored in blue. By doing so, we will have a multiple scale PNM where the convective transport and dispersion is modeled using the reactor scale PNM, and the diffusion and reaction is modeled using the particle scale PNM for all the particles in the packed bed. So we will have a multiple scale pore network model. Here you can see the axial concentration profiles at different time steps for a condition where Thiele modulus is equal to 1 and Reynolds equal to 50. We can see that by time how the concentration evolves inside the packed column. Also, we compared the cup-averaged axial concentration profile from PNM to the one from a 1D model to validate our multi-scale PNM. Also here, the blue dots, they represent the concentration in reactor scale pores. If we take a deeper look into the concentration map, we can see that there is a crescent shape profile. And this is because of the flow maldistribution that we discussed earlier, that close to column wall, there is a higher flow compared to the central region of the column wall, and we can clearly see it here. Now, the axial concentration profile, which is the steady state, and the comparison with the 1D model that we can see here. So for the conclusion, here we developed the reactor scale pore network model for modeling the hydrodynamics and species dispersion in a packed bed reactor. We also developed a particle scale PNM for modeling the combined reaction and diffusion in porous catalyst particles, and coupled these two pore network models. We also validated our reactor scale PNM by comparing to MRI results. So for the outlook, we can implement other transport phenomena, especially heat transfer, on our pore network model to make our multiscale model be able to capture hotspot formation, which is quite important. And we can assume other particle shapes, such as spherical, such as spherocylindrical, cubical, and etc. And also we can also improve the PNM prediction accuracy. This also could be a nice outlook for future research. So at the end, I would like to thank our research group in the Chemical Engineering Department of TU Eindhoven. And so I would like to thank my supervisors, Dr. Kai Bast, Dr. Frank Peters, and Professor Hans Kuipers. And thank you very much for your attention. If you have any questions, I'm happy to answer.
Right, thank you, Ali, for a wonderful presentation. I was very impressed by the scope and the depth of your work, spanning from modeling to experiments. It was very impressive. Thank you for sharing that.
Thank you very much.
Those of you in the YouTube, watching this on YouTube, if you have any questions, please write your questions in the chat. And while those of you are maybe typing, I have few questions from myself. So
yep.
The first question was in slide number 10. I think you were comparing the pore network modeling to CFD, and I know it showed a good match,
yep.
but it seemed
yep.
There was a little bit of a discrepancy. So
yep.
could you comment on what caused that discrepancy? Is it the local flow or pore scale flow, or what is it?
Yeah. Actually, that's a really nice question, I can say. Also, we addressed this question also in our publication. So the reason for this discrepancy between PNM and PRCFD is related to the definition of pores and throats, especially close to the column wall. And we noticed that the definition needs to be improved close to column wall. But if we compare for example, the cumulative flow rate from for example, from this peak here to the one from PRCFD, we can still see that the comparison between PNM and PRCFD is quite good. So it just relates to the definition of pores and throats, you can say.
I see.
Yeah.
I see. And since you mentioned about the column wall, I had a follow-up question related to that. So in the later part, you mentioned about the flow distribution showing a higher flow velocity near the column wall. So
yeah.
I'm not so familiar with the packed bed reactor system. So and when I normally think of a flow in a conduit, I think of a parabolic distribution of flow.
Yeah.
With the center part having the higher
Yeah.
flow velocity. So is the reason for the flow near this column wall having the higher velocity is because the porosity is higher there? And
Yeah.
do you think is it due to the artifact of the system size having 2 and 1 millimeter, which can be a little smaller? I'm not sure the real scale, the real size of the packed bed columns, but what's your opinion about that?
Yeah, that's true. So the reason we have a wall channeling, it's also called the flow channeling close to the column wall, is because of that we have a higher porosity there, and also the pore shape is also different from what we see in the center of the column. And the packed beds that we are investigating here are the slender packed beds, which are called. And so in the slender packed beds, the ratio of column diameter to particle diameter is usually very low, lower than 10. But in other applications, like in other packed bed, you can find, for example, a packed bed reactor where the column to particle diameter ratio is like 50. And there, the wall effect is not that intensified as what we have here in the slender packed beds. And so why slender packed beds are used? These are used for like really highly exothermic reactions that we need to have a proper heat management of the chemical reactor that you're using.
Yeah. Thank you. And I don't see a question from the chat yet, unless we have another question from our organizers. I wanted to ask one more question because this was quite interesting to me. And you said you have plans to implement different shapes of the particles, and I was just wondering how the shape of the particle can impact the reactor scale process, because the contribution of single particle, if I imagine, can be small, and I was just wondering what degree of what magnitude the shape effect will be in terms of when we look at the whole process in the reactor scale.
Yeah. So so the easiest answer for this question will be that if we use different particle shape, it will give us a different porosity distribution in our packed bed. Yeah, actually, also in one of our previous studies, we investigated this. So we had packed beds composed of cubical particles and also cylindrical particles, so particles with flat surfaces. And we noticed that the different shapes, they really impact both the porosity profile inside the packed bed and also the radial velocity profile inside the packed bed.
So then would you expect, if the shape of the particle is different, but the porosity is kept about the same, would you expect about the similar performance, or?
It is not only the porosity, because the particle shape, for example, particles with flat edges, they also affect the hydrodynamics, like hydrodynamics close to the particle surface, especially where we have edges. So I can say, it will affect it, and the porosity is not the only factor. It is the most important factor, I can say, but not the only factor.
Yeah, thank you for the answer. I look forward to your future work.
Thank you very much.
And I don't think we have more questions in the chat, so I think we can conclude the first part. And Mohammad, I think you can take over now.
Okay, thank you very much, Ali. And now we can move on to our second speaker. Our second speaker is Dr. Eleni Stavropoulou. She is leading the carbon capture and storage, or CCS, activities at the Laboratory of Soil Mechanics in EPFL, Switzerland. Eleni received her PhD in geomechanics in 2017 from University of Grenoble in Alps in France. And her research focuses on the characterization of natural geomaterials in the context of contemporary engineering, such as geological CO2 storage. She has been particularly interested in understanding the impact of microscale processes on the macroscopic responses by systematically using advanced imaging techniques like X-ray tomography. Thank you, dear Eleni, for joining us today, and the floor is yours.
Hi, everyone. Hi from Lausanne. Thanks, Mohammed, for this nice introduction. And I would also like to thank the entire organizing team for inviting me to give this talk today. So what I'm going to talk to you about straight away is about our work together with Cesare Griner and Lies Lalui on the CO2 storage in basalts, and more precisely on the impact of mineralization on the flow properties of the material. Okay, so CO2 can be stored permanently in basalts through mineralization. What is happening is that as we inject CO2 dissolved into water, this reacts with some favorable minerals of the material to form stable carbonates that they look, I don't know if you can see my cursor, that they look like these white lenses. Yeah, you can see them. These lenses here that in this basaltic core that I'm holding. There are several advantages for storing in basalts. First of all, mineralization happens fast. I don't know if you're familiar with geological CO2 storage. This first diagram is a typical diagram that shows the different trapping mechanisms contribution with time. And as time increases, the storage security increases. And so in let's say, traditional geological storage in deep saline aquifers, we see that to achieve secure storage and stable storage, we need multiple decades. Instead, with mineralization, permanent storage is supposed to happen within already a couple of years, which makes this technology very attractive. In addition, there is a much lower risk of leakage and induced seismicity. This is because the dissolved CO2 that we inject is denser than the pore water that exists in the material, and therefore it's not buoyant. It doesn't have the tendency of going upwards. They're like the pure CO2, and that makes leakage risk much significantly lower. The total cost of this way of storing CO2 is much lower as well, because the injection is happening usually at shallow depths, around 300 to 400 meters. And finally, there is a large storage potential worldwide, both offshore and onshore. Now, there are still some open questions that we've been trying to directly or indirectly reply in this work that has been has taken place within the DEMWAP Karma and Storage project. And these have to do, first of all, with the impact of seawater on mineralization. Up to recently, most studies and real injection of CO2 was concerning CO2 dissolved into fresh water, which is, as you can imagine, not the most ecologically friendly and viable solution. So now we're really going towards investigating usage of seawater that we have also in abundant quantities. Then we also try to address and understand in this work where mineralization actually takes place, what is the storage efficiency, and finally, what is the long-term performance and safety of this technology. So in the first part of this work, we actually studied the material itself. We received 7 different basaltic cores that you can see here from Iceland, from a site near to the injection site of Carbfix. As you can see here, the plan is that CO2 captured in Switzerland will be transferred all the way to Iceland and injected there in the basaltic formation. And so what we wanted to target with these cores is to have an as variable a representative study in the lab as possible. This is why we chose cores, as you can see, with significantly different porosity, color, and different structure. So as a first measurement, we wanted to understand what is the different porosities that these cores have. This we measured both in the lab and through X-ray tomographies in a resolution of 50 micron per pixel. And as you can see, there is a rather, if we plot here the measured porosity with the depth of these cores, we can see a rather variable behavior. There isn't really a trend, unlike what we have in sedimentary rocks, as that you have lower porosity as you go deeper. So this variability is not only between the different cores, but is within a single core itself. So if you see here the 3D rendering of an X-ray scan, this is a 3D volume, and we have a look at 3 different slices, horizontal slices at different heights. You can see completely different porosity, pore size distribution. We have some huge pores, some localized areas of big porosity and very small, and also in other regions with very, very small pores. So this is something that we really need to take into account to representatively study and model this material. Well, we can see these pores. We're obviously limited by the given resolution, which is 50 microns per pixel. However, there are pores also below this resolution. And as you can see here, indeed, we can measure pores. We can measure a dominant microporosity of an average 1 micron in this material using, for example, mercury intrusion porosimetry, MIP. So in addition to these very complex porous structures that we can see here from our scan, we know that there are also smaller pores and structures that we can't really see with this technique. Okay, knowing all that, we go now to the lab and actually try to test this material, inject CO2 and see how it reacts with the dissolved CO2. What we did is that, for instance, we took our sample. As I said, we pass it from the tomograph, from the X-ray tomograph, to have the initial pore structure. This we did it for all pores, and so we have the real 3D porosity of the material. We then put it in our hydromechanical cell to perform a flow test and assess the flow properties of the material. So initially, we applied an isotropic confinement of 5 MPa. And then we saturated our sample with saline water, so with seawater, in order to assess the hydraulic properties, for instance, permeability at its initial state. More precisely, we applied a hydraulic gradient between the 2 sides of the material of 1 MPa, and we were able to measure permeability. After that, after we assessed these properties, we injected CO2 dissolved into saline water. We made sure from our porosity measurements to inject at least twice the porosity volume of CO2 dissolved into seawater. And what we did is that we then closed the valves and we let the material interact with the CO2. During, at least we had a lot of cores, we targeted a minimum exposure time of 1 month, but as you will see later, we also have tests and results of much longer duration. So after that, we resaturated again, we flushed again our sample with fresh saline water, and then we reassessed the hydraulic properties and permeability of the material by repeating this constant hydraulic gradient between the 2 sides of the sample. Finally, once we have this measurement, we pass again our sample through the tomograph, so in order to be able to try to see if we can capture any changes in the pore space that we have initially characterized. So if we plot now, if we look at the results between the total porosity and the measured hydraulic conductivity at the initial state of the sample, you see here pre-CO2 exposure, we see a kind of a slight trend of increasing flow properties, increasing conductivity for higher porosities. You can see that there is an increasing variability for higher levels of conductivity, which means that, for example, we have similar conductivities for completely different porosity levels. And this is a first hint that tells us that what it really matters is the connected porosity and not the total porosity of this material. If we now plot the measured values of the post-CO2 exposure hydraulic conductivity, you see here the different exposure time for the samples. As you can see, as I said, the minimum is 1 month, but we have samples that they were exposed up to 3 months. The results are these, the red triangles, but we can't understand much. So let me explain to you for the given samples and the given durations, we were able already after 2 months to see some significant changes in flow. And more precisely, we observed a decrease of permeability and conductivity by 2 or even 10 times after exposure to CO2, which is quite significant, in particular using seawater. Okay, these are the results themselves as we obtained them from the lab. Now we need to try a little bit to go a bit further. We have a lot of information, localized information about the exact pore network, well, pore structure, if I may say. So we can use this to try to understand a little bit better where mineralization might have occurred. So to do that, we used pore network simulation. It's great that Ali talked about pore network models just before, so I will not have to go into too many details. So let me explain to you the protocol we followed for this simulation. So we use the pore network model directly using as an input parameter the information, the exact information of the material we have from our X-ray images. So you can see here the 3D volume of the solid. So you see here in light gray is the solid, and in dark gray is the void, the pores. From that, we can obtain the pore volume. Now is the inverse. So we have the pores in light gray and the voids in black. And this is our input data to build and fit a pore network. To do that, we use the open source OpenPNM software that uses an algorithm that is called the SNOW algorithm, but you can find a lot of information online as you wish. So we were able, from our real pore structure from the X-ray image, to fit a pore network. And based on this algorithm of OpenPNM, we can also, as in a similar way that Ali showed before, have define an initial network connectivity. So we can have we can obtain the throats that they connect the different pores. As you may suspect, this connectivity of the given network is quite poor. We were not able directly from this algorithm to perform the flow simulation along the total height of the material because our network was not fully connected. This is related to the distance of the pores, the resolution, obviously, that we have from our image, but this is a result. So in order to overcome this problem, we manually added some additional throats to have to create a fully connected network and perform our simulations. Now, through the simulations, we're trying to target, as I said, CO2 mineralization. The reasoning behind this adding these additional throats is to represent basically the resolutions below the X-ray tomography that we can't see. We know, as we saw before, that there are pores lower than 50 microns that we cannot see, and so these additional throats we are going to consider that they represent the microporosity of the material, or what we call solid matrix porosity. So we're trying to fit the stitch throats with a diameter that is obviously lower than 50 micron. And in order to reproduce our experimental results in these 3 cores that we saw some real change in the flow properties, we managed to reproduce them numerically by fitting a micro pore diameter of an average of 4 or 5, let's say, microns. So well below 10 times lower than our X-ray resolution. Okay, that makes sense. It's a hypothesis, of course. But now, basically, with this approach, what we do is that we simulate our material with a double scale porosity, a macro and a micro. This can actually help us to better understand where this mineralization might occur. So mineralization, in case it happens, it causes precipitation and so some pore reduction, and eventually that's what we saw with this flow decrease. So we have now this model. If we go and try to touch the macropores, so try to reduce their diameter, their size, we see that there is really no impact on the flow properties of the material. On the contrary, if to reproduce the post CO2 exposure results that we obtained in the lab, the only way to do it from this double scale model that we have is by reducing the micropores that we have added, and this can mean that we need to perform reduction as much as even by 43% in diameter, which is quite significant. Okay, this is good. We have, this is a first hint of where mineralization is more prone to occur. We show here that indeed it's not the big pores that the impact flow, and it's rather the small pores. And we have, as I said, all this rich information and this pore network model that we can see some more precise localized phenomena that they happen in our material. So here we see the pore network model of our samples before and after CO2 exposure, and this is the pressure front, the pressure propagation, 2 - 1 MPa in each side of the material. In the post CO2 exposure, you see here in the previous post CO2 network model, we see a pretty, let's say, continuous pressure front. Here we see some localized, very interesting phenomena. For instance, this lens here, where we see that the pressure, it does not propagate through this area, and this might hint at pore clogging locally in the material. Or even on the contrary, we have again some pressure build-up lenses in a different core. So we do see that the macroscopic results from the lab, but with these techniques and methodologies, we can, for instance, target in the microscale where things exactly happen and are more prone to occur. So to conclude, I hope I'm not too much over time. What we were able to see in the lab already after 2 months is that mineralization might occur. This we deduced by means of reduction in flow, but we have some complementary measurements that related to pH changes and conductivity that you can find online in our published work that I'm going to share at the end of my presentation, and also. We were able to measure decrease of flow by almost 10 times. To study this the potential impact of mineralization on the flow properties and these changes on the flow, we considered a double porosity model, considering macro and micro porosity. And we found that mineralization is more prone to take place in the small pores, and this meant reduction by up to 40%. Finally, these tools that we developed and we used were able to show us that, to prove that carbon mineralization can result in localized pore clogging and pressure buildup, which is something that if we're trying to upscale might be quite critical. So now if we want to try to generalize and discuss a little bit about, let's say, larger scale implications for CO2 storage, the first thing that we can deduce from this study is that, first of all, you see, we saw flow reduction already very fast. So there is a high storage potential indeed through mineralization, on the condition, however, that flow is not prohibited. Then the other thing we need to take into account is that we tested cores, intact cores. So these represent the intact rock material in the different locations in the field. So by taking this into account, an ideal scenario, and this is actually what is happening in Switzerland and Carfix, is injection of CO2 in highly fractured zones to ensure that flow is not prohibited. And our work, our contribution is this front here of the intake material that eventually will start mineralizing and create a mineralized front. This whole work has been very recently published. You can go and look for it. Some of the X-ray tomographies and network simulations have been uploaded online, so you can go and play with them. And I would like to thank you for your attention. I'm very happy to listen, to reply to your questions if you have any. Thanks.
Thank you very much, Eleni. It was excellent talk. I enjoyed it a lot. To keep it a bit educational, can you tell us more about how you handled dissolution and precipitation reactions in your simulations and how you coupled it with the PNM?
Thank you. That's a good question, and the reply is very simple and short. We didn't take into account any let's say geochemical reactions. Our approach, as I said, is an indirect way of studying mineralization. That's why I've been insisting saying potential mineralization, because basically we assess the hydraulic properties of the material before and after. As I said, and I haven't included it here, but well, actually I have it as a backup slide. We have some additional pore fluid analysis after the exposure, where you see some considerable decrease of the conductivity, electroconductivity, and increase of the pH, which go, let's say, I will not say prove, but go towards the direction that mineralization has actually occurred, and what these changes in the flow is because of eventual precipitation in the pore structure. But for our simulations, we just repeated exactly our tests, hydraulic tests in the lab. Okay, so we just performed this flow. Basically, it's Darcy law, basically our simulations, and that's it. But eventually, that would be very interesting to go further and do that.
Do a reactive transport modeling on the X-ray images.
Yeah,
that would be extremely important. Another question.
Sorry, if I may say so. Well, you have the results. I'll stay here. You have the results. You have the tomographies. I mean, everyone is very welcome to use them and do this exercise or do it together in the future.
Yeah, so if you are into the reactive transport modeling, I certainly encourage you to go and download this Zenodo data set and do a reactive transport modeling together with Eleni, because it is such an important research topic. And I'm sure that if you do this, you will learn a lot, and also it would be a great importance for the scientific community. So I hope people will contact you, Eleni.
Thanks, Mohammed.
From the X-ray images, do you see any increase in porosity? I mean, the dissolution, comparing bigger pores and smaller pores. Do you see any difference?
Yeah, that's the tricky part. That's what we hoped that we see with, having our samples scanned before and after. We were hoping that we will see, pores or zones where we really see some changes. Well, the pore network model somehow indicates, if not proves, that the pores, they don't really matter. Well, it's not that they don't matter, but we can't, they haven't really changed. And indeed, it's the micropores that we cannot see where things happen. Now, in terms of dissolution that you mentioned, so usually dissolution is what is happening first, and then we have eventual precipitation. In the cores where we saw reduction, of flow, we only have the scan after the reduction, so we cannot have an image of when the solution might have occurred. We have directly the end. But we were not able to have some, let's say, quantitative results, quantitative measurements on the changes of the porosity. In this publication, there is that's why we've put it in the appendix. There is a session where we discuss that, where we show, for instance, some zones where we see some decreases. But as I said, I was quite skeptical on the quantitative nature of these results, so that's why I don't insist much on them. But yeah, there are some indications, but yeah, it's hard to talk about it in a quantitative way.
Yeah, nonetheless, if we want to unlock the potential of carbon mineralization in basalt or in mafic or ultramafic rocks, such kind of a study that you did is essential for this for exploring this technology and unlocking the full potential of carbon mineralization in basalt. So thank you for coming and presenting your research today. We really appreciate it. Now, I guess we can wrap up the session today. Our next talk in the 20th of August would be by two different speakers, two diverse talks by Sabrina Volponi on the interception history drives colloidal transport variance in porous media. And the second talk would be quantitative characterization of carbonate pore system using seismic and well log data. So it's going to be quite a diverse session in August. With that, I would like to wrap up this session, and I want to announce that if you are interested in the porous media activities, there would be an election in the Interpore Society, and there is free spots for the Student Affairs Committee. If you are interested in joining a Student Affairs Committee and get involved with the student focus activities, contribute to the annual meetings, activities, events, and educational programs that the SAC is organizing for the porous media people all around the world, please get in contact with us, and then we can instruct you how you can self-nominate or nominate a colleague. This is the Porous Media Tea Time Talks team, and with that, I would like to close the session, and thank you all for joining us today. Bye-bye.